Lab 1 wrapping up okay for people? Any like last minute lab 1 questions? Okay. Has anyone been able to get a single node simulated yet?
Yeah, we were able to get one node running.
Okay. Any gotchas or surprises or anything, or did it go pretty well?
Just kind of going off of the lecture, like node description and the formula, it seemed to work fine. At least we think so. We got like the decaying like sign effect.
Okay.
Was there any hassle, any problems with overflows or anything special you had to do to avoid overflows?
Yeah, when we did the one node, we had to be very careful and basically move in all of our shifts as far as possible, like distribute it over all the additions in order to avoid overflows with the 1.17 format.
Do you guys have the, do you have a row set as a fixed parameter, or do you have the nonlinear row implemented?
We have it as a fixed parameter for now.
Okay, I think that's a good place to start.
Mm-hmm.
Cool. Any other concerns from anyone? Anything anyone else wants to bring up? Okay, so I want to talk today about generate statements and go through an example of a generate statement. And then with time permitting, I'll go through some reasonable choices for the parameters for this equation. So how do you select a row naught, for example? How do we select an appropriate nonlinear gain? And how do we set initial conditions? Those sorts of things. But I want to start with the generate statements. And I'll start by showing you where you can find some documentation on this, because you might want to read the documentation for the generate statements in particular. But if we go down to the, I have to remind myself, within Verilog, the Sutherland HDL quick reference. Within this, we can take a look at generate blocks, page 20. So we'll go down to page 20. So these generate blocks are the means by which you can avoid writing thousands and thousands of lines of Verilog. And what they allow you to do is to create these variables that they call genvars, which exist only at compile time. So, which is to say that when your code is getting compiled, the compiler will look at these genvars and these generate blocks and use them in order to construct a whole bunch of Verilog. But the genvars themselves get abstracted away after compile time. These generate blocks turn into a whole bunch of Verilog. Within these generate blocks, though, you can do a bunch of stuff. So you can do things like declare variables, you can instantiate modules, you can wire modules together, all of which is going to be really relevant for constructing a bunch of basically identical copies of the column drum solver. But because these are only interpreted at compile time, that carries some implications. One of which is that all of your, if you are allowed to have conditional statements within these generate blocks. So you're allowed to do something like within the generate block, say, if some condition is true, then do this, and if not, then do something else. So you can have if-else statements, you can have case statements, you can have for loops. The thing to keep in mind, though, is recall that these generate blocks are actually creating hardware. So for that reason, all of your condition statements need to be, your condition variables need to be constant expressions. That is to say, they need to be evaluatable at compile time. If you think about this in the case of something like a for loop, right? Your for loop, every time you go through it, it's generating more hardware. So when you're generating that hardware, the compiler needs to know at compile time how much hardware to generate. So you can't have some dynamic variable within your for loop, because that would suggest that you were sort of creating hardware during runtime, which doesn't make much sense, right? So all of these genvars and all of your conditionals need to be constant expressions, and the genvars themselves need to be strictly greater than 0 or positive integers. It's the limitation on the genvars. And we'll go through an example to look at some of the syntax that's involved here, because it's not difficult, but is worth taking a look at. So anyway, here's where the documentation lives. And I wanna really introduce this by means of an example. Questions so far? So generate blocks, a method for generating lots of Verilog. So for example, let's say that we wanted to construct a shift register. So let's say we wanted to construct something that looks like this. What I would like to do is construct this hardware without a generate statement, and then construct exactly the same hardware with a generate statement, so that it is hopefully obvious sort of what we're replacing with the generate statement. So let's first construct this circuit without using a generate block. So that's going to look something like this. And I'm going to build this in such a way that that when I do it with the generate block, I can sort of just remove a chunk and replace it with the generate block. So if you were to actually construct a shift register on your own, you might do it a little bit differently than the way that I'm about to do it. But I'm doing it in this way strategically so that hopefully it's obvious the part of this Verilog that can be replaced with the generate statement. So let's suppose that we want to make some module called shift that takes an input wire, it's a clock, and an output wire that we'll call Q. We'll declare some 8-bit wire P through which we'll be shifting. And then I want to be able to shift things into the front of P so that the output will change, because I'm going to model all of this in ModelSim, and I want the output of the shift register to actually be toggling. So I'm going to do that by means of just a 4-bit counting variable. So we'll declare a 4-bit reg called count, which we'll initialize to 0. And then we'll just overflow this. We'll say always at pos edge of the clock. We'll say that count gets count plus 1. And then we'll assign the first bit of P through which we're shifting the upper bit of count. So what that means is what will that be? Every 8 clock cycles, I believe, we'll toggle P0. So P will go from a 1 to a 0, and then 8 clock cycles later, it will go from a 0 to a 1. So on the output of this shift register, we should see the output toggling every 8 clock cycles. Okay, and then we'll actually create the shift register. So we'll declare some 8-bit register that I'll call preg. and then always at pos edge of the clock, we'll do a bunch of repetitive stuff. So we'll say preg1 gets p0, preg2 gets p1, preg, oops, already made a mistake, 2 gets preg1, 3 gets p2, preg4 gets p3, preg5 gets p4. If this is boring, that's kind of the point. Preg6 gets p5, and preg7 gets p6. And so at every positive edge of the clock, we're shifting through this shift register, right? And then we'll assign p from 7 to 1 equals preg from 7 to 1. And then, oops, forgot a semicolon. And then we'll output from this module the final bit of p here. This p7 will be output. So we'll say assign q equals p7. Semicolon. Does this make sense? Right, so all we're doing is we've declared some wire that we would like to shift values through. We want to create values to put into that shift register. So we're just doing that with a 4-bit register that we overflow. And we're pumping the upper bit of that overflowing register into the bottom of the shift register. And then at every rising edge of the clock, we shift through this shift register, right? And I'm being a little bit careful here because within this clock logic here, I need to be using registers as opposed to wires. So I'm doing a little bit of footwork here just to make sure that I'm using registers where I need to be using registers and wires where I need to be using wires. In this particular case, right, the repetitive bit of Verilog here is not super complicated, right? But you could imagine a situation like Lab 2, for example, where the repetitive Verilog is significantly more complicated and the interconnects between all that Verilog is more complicated. So this would start to get error prone. So what I want to do then is consider how we might build exactly the same circuit using a generate block. I think I just saw a chat pop up. Let me see. Is there a reason the P wire is 9 bits? Probably because it's a typo. Yeah, thank you. So the way that we would do this.
Can I ask, so the output of this, the output of this module is going to be 8 ones, then 8 zeros, then 8 ones, and so on.
Correct. Right? So we'll build a separate flip-flop module. We're gonna build the hardware that will stamp down a bunch of times. We'll put that hardware that we're gonna stamp down a bunch of times in its own module. So we'll create some module that I'll call dflop, which takes an input clock wire, takes data in, and then returns data. And this is going to be a very simple module. We'll have some register called out, and then we'll say always at pause edge of the clock, we'll say out gets the value of the data D that we've passed into the module. And then we'll assign our output Q, assign Q equals out. Does that make sense to people?
Is the out keyword where you define Q, should it be output?
Yes, thank you. Okay. We can then use a generate block to stamp down and connect a bunch of copies of this module, which is going to look like the following. The first part of this is going to be exactly the same as before. But then we'll use a generate block. So we'll say generate, and then we'll say genvar n. Turns out you can declare these genvars either in the generate block or outside of the generate block. The compiler's okay with either. I think it's a little tidier to keep them inside of the generate blocks. I think it makes it a little easier to keep track of where things are, but it won't throw an error if you don't. So then we can say for our genvar n equals 0, n is less than or equal to 6. Looks a lot like C. We'll say n equals n plus 1, begin, and then we have to give this a name. I'll call this flop gen. And then within this for loop, we will instantiate our dflop module. So we'll say dflop. We have to name each of these instantiations. I'll just call it U. And we'll say clock. We'll go to the clock. The data that we're going to pass in is going to be our wire P indexed into N. And then Q will attach to P n plus 1. And that for loop and generate end module. Okay, so we've started a generate block, created one of these genvars, which we've called n. We've created a for loop where we take from n from 0 up to 6. And we've named that, we've given that for loop a name. And then within that for loop, each time through the loop, we're instantiating one of our dflop modules. And we've hooked up the clock to that dflop module to the clock. We're passing in the nth bit of P, and then we get out the n plus first bit of P. Which is hopefully it's clear that that is building a shift register, right? So this is providing us with a method for generating arrays of modules and arrays of connections between modules. That's what this generator has allowed us to do. In this particular example, the module that we're generating an array of and that we're generating an array of connections between is quite simple, but it needn't be. This could be a very complex module. And with a generate block, you can generate an array of those complex modules and an array of connections between those modules. So for example, if this module described one column of your drum, then with a generate block, you could generate an array of columns of drums and an array of connections between those columns. And like we saw in the previous couple of lectures, those connections are going to be hooking up the left and right inputs to the compute modules in each column. So by using one of these, you can write a module that describes one column, and then you can generate a bunch of copies, and you can generate all of the connections between those copies. And even better, right, we talked about how you can put condition statements into these generate blocks. So you can even pass in, you can even enforce boundary conditions within these generate blocks. So if, as you're looping through some sort of a genvar for loop here, if you reach your final column of the drum, you can have a condition statement pass a zero boundary condition in to that particular instantiation of the module. Because that module is probably going to be, you know, tens of lines of Verilog at least, right? So you're saving your, if you're generating 170 columns, this saves you a whole lot of lines of code, right? And a whole lot of potential mistakes. Questions about this? Just in case you're skeptical, I thought I would show in ModelSim, I have a simple test bench put together. All this test bench is doing is generating, simulating a 50 megahertz clock, and then it is taking two output wires, and it's instantiating two devices under test. One's called shift, and the other I've called shift 2. These are the two versions of the hardware that we just looked at. So shift is the shift register without using a generate block. This is exactly the same Verilog that we just wrote in the Jupyter notebook. And then shift 2 is the version of the shift register that uses this generate block. Okay, which means I've created a little D-flop module down here. All of this Verilog is exactly the same that we just wrote in the Jupyter notebook. So the expectation, this should be building exactly the same hardware. So we can simulate this. And take a look. So before I run this, it's good to ask yourself before you do things like this, what output do I expect? So the expected output here is that we should see the output of the shift register, the outputs of both shift registers should be toggling low, high, low, high, low, high every 8 clock cycles. And they should be doing that precisely together. So we'll see if that's what we see. Okay, and this is about what we expect. So we can see the output of the shift registers toggling exactly in sync. And if we could count the cycles here. 1, 2, 3, 4, 5, 6, 7, 8 cycles per toggle. If we really wanted to look at this, and I don't have the thing set up to show this, but you could, within Quartus, once your Verilog has compiled, go and take a look at the actual hardware that it's generated and convince yourself that the hardware being generated with the genvars and the hardware being generated without is the same, it's generating the same hardware. If you'd like to do that, you could go do that. Does this make sense? So it's mostly a question of making sure you've gotten the syntax right. Any questions about these? Okay. If there aren't any questions, then I'll talk next about choosing parameter values. And let's start with row. So let's recall the equation for row effective, which is to say the nonlinear row, which looked like row effective is equal to the minimum between 0.49 to enforce that Courant condition, right? If row or row effective exceeds 0.5, then our drum becomes unstable. So it's the minimum between that and some row naught plus the amplitude of the center node squared. I'll designate that with U sub C, the center node, times some tension gain squared. Okay, where we must enforce that row effective is less than 0.5. So then a question that's already come up in lab is, what are some appropriate values for row naught and for GT? And we want to be able to hear the nonlinearity, right? So if we want to be able to hear the nonlinearity, then what we would like for this nonlinear part of this term, the U center squared, GT squared, to change row naught by something between like 10 to 30% or so. Maybe even a little bit more, maybe up to like 50%. The more that changes, the more of a nonlinear pew you'll hear, right? So, so we'd like for UC squared GT squared to change row effective by, we'll say 10 to 50%. So, so perhaps a place to start is we can choose a value for row naught. Row naught that is safely in the middle of its range. Just to say about 0.25, right? If row naught has to be between 0 and 0.5, it can't exceed 0.5, then we could say perhaps a good choice for row naught, at least to start, and this can be something that you can play with and see what you like the sound of, but a place to start would be row naught equals 0.25 or so. Okay, so then we'd like for UC squared GT squared to be 10 to 20% of 0.25, and recall that the amplitudes have a range of -1 to 1. So that means that we want for UC squared, GT squared to be somewhere between around 0.025, which would be 10% of 0.25, and 0.125, which would be 50% of 0.25. So this implies appropriate values for GT squared in the range of approximately 2 to the minus 3 to 2 to the minus 5 or so. Does that make sense? So if we have rho naught as 0.25, and if we select our GT to be somewhere in that range, then even for amplitudes that are at the edge of the possible range, which is to say amplitudes around 1 or minus 1, then with GTs selected in this range, we won't overflow we won't exceed 0.5 for our rho effective. But we will get an audible amount of change to rho for different amplitudes. It'll change that effective rho by 10 to 50% so that you can hear some actual pitch glide. Okay. So then there's another constant to think about. What about the constant eta delta t over 2? I'm going to give an answer for this and then justify it. So an appropriate choice for eta for this parameter is in the range of somewhere around 2 to the minus 9 to 2 to the minus 10, maybe even smaller. Why? So recall that eta is telling you about the damping per cycle in our drum. So if you imagine that we have a drum that's running at 100 hertz and we hit it, how long is that drum going to ring? In real life, how long does a drum ring? Probably maybe on the order of 1 to 3 or 4 seconds, right? So that means it's going to be ringing for 100 to 300 cycles if it's running at 100 hertz, which implies a per cycle damping that is much lower than 0.01. So somewhere in the range of 2 to the minus 9, 2 to the minus 10 seems to sound right. If you make this too high, the effect is going to be, you'll start your drum and it'll maybe go down and then flat, right? It won't ring at all. If you make this extremely low, it'll just ring and ring and ring and ring and not damp out. And that doesn't sound physical either. Right? So somewhere in this range seems to sound right. Questions about that? Okay. So another question that I've gotten in lab is how to set initial conditions. So I want to go over what are your options for setting initial conditions. You have a few. One option is if your drum update is taking place in some sort of a state machine that's going through the rows of the drum, you could have some initialization state machine that runs before your audio state machine that steps through the nodes and does some sort of a calculation at each node in order to come up with an initial amplitude. So that calculation, it will likely be something like, what is the distance? It may be proportional to the distance of that node from the center of the drum. So perhaps the center node has some amplitude, and then as you move 1 unit away, or as you move n units away, you subtract n times some constant from that initial amplitude, which would give you sort of a linear pyramid in the middle of your drum. Or perhaps you do something a little more complicated where you do some sort of an exponential fall off. So maybe you have a flat raised square in the center of your drum that exponentially falls off at the edges. A few different options. So I would say option 1 is a state machine that loops through nodes and calculates initial amplitudes based probably on distance from the center of the drum. So that would be calculating initial conditions sort of kind of online in some sense. The other option is you could come up with a set of initial conditions beforehand in MATLAB perhaps, and store those initial conditions in a ROM table or in memory of some sort on the FPGA, and then at reset, go through that memory and set all initial conditions according to the stored values. So option 2 would be store your initial conditions in SDRAM or a ROM table. And we've seen before these ROM tables. If you recall the DSP example that I showed a few lectures ago that did direct digital synthesis of a sine wave, the values for that sine table was set up as a ROM table. I can show you that if you would like to see it again, but it's on the DSP page. You can see how those sine values are stored. That would be how you would set up a ROM table for your initial conditions.
That ROM table does take M10K blocks, however. Unless you explicitly tell the compiler to put that block in logic, it will automatically be compiled to M10K blocks, which means you can't use those for state variables. But it may not be a very big table.
Yeah, it's maybe worth clarifying that your initial conditions, most of the nodes on your drum's initial conditions might be 0. So you might have something like some square area that's significantly smaller than the total size of the drum that's getting initialized. That area needs to be large enough to not alias, but it can be significantly smaller than the total size of the drum. So you maybe only store 20 by 20 nodes worth of initial conditions, and then at reset, move those initial conditions to the center of the drum, or to anywhere on the drum, really, if you wanted to do an off-center drum strike. Another option may be to read this from the HPS. So at reset, you could potentially calculate initial conditions on the HPS side and then send those initial conditions over to the FPGA. That might enable you to do things like come up with really nice sort of Gaussian initial conditions that you could calculate on the HPS and then send over. You could do that too if you stored Gaussian initial conditions in memory, but I would say this is another option. So how do you pick? You might think about which of these options is consuming resources that you would otherwise like to use to build a bigger drum. It's maybe one thing you want to keep in mind. You might consider which of these options is easier. That's another important thing to keep in mind, right? There's a lot of problems to solve, so deciding which are the problems you want to face is a good thought process to go through. A few different options. Questions about this? Okay. Then the next thing I will, so I could do one of two things next. And if I don't, whichever one I don't do now, I'll do next time. I could either show you in some more detail the block diagram for the Wolfson codec, the actual audio chip that you're writing to. There's some interesting features of that we could take a look at in a little bit more detail. Or if it's useful for folks, I can do a review of fixed point signed multiplication. Because we're changing, in lab 1, we were using, what was it, 7.20 fixed point. Now we're going to use 1.17. So you need to write a new signed multiply fixed point module. Maybe that's trivial for people, or maybe it's worth taking another look at. Let's take another look at it. There's only 5 minutes left, and I think this is one of those things that if we spend a couple minutes just looking at it again, it might save you 10 minutes in lab. Or maybe not, but that's okay. So I'm going to pull up the notes from, I think that was in lab 1 information. Yes, I wanted to just review this. So you're going to be putting together a signed multiply module that looks a lot like this, but you'll be selecting, your inputs will be a different size, and then you'll be selecting different bits for output because you're doing multiplies with fixed points that are different size. So I just want to remind people that in this particular case, when we were doing a fixed point multiply of two 7.20 fixed point numbers, what 7.20 means is that there are 7 bits above the binary decimal point and 20 bits below the binary decimal point. When we multiply two of those numbers, we get an intermediate value that is twice as long as either of the values that we just multiplied. And that intermediate value has 14 bits above the binary decimal point and 40 bits below the binary decimal point. And then if we're doing a signed multiply, the actual bits that we want to grab include the most significant bit, because the sign information lives in that most significant bit. And then in the case of 7.20, we want to grab the bits that are hugging the binary decimal point. So the 6 bits that are directly above the binary decimal point, and then the 20 bits that are below that binary decimal point. So 7.20 times 7.20 yields 14.40. We select the sign bit, and then we select the most significant bits around the binary decimal point. So the modification that will be required for lab 2 is we're going to be doing signed multiplies of 1.17. 1.17 means 1 bit above the binary decimal point and 17 bits below the binary decimal point. That's going to create an intermediate value with 2 bits above the binary decimal point and 34 bits beneath the binary decimal point. And you will grab the sign bit and then the 17 bits that are directly to the right of that binary decimal point. Makes sense? So if each of these numbers is 18 bits long, that means the intermediate number after the multiply is going to be 36 bits long. So you'll grab bit 35, the sign bit. You will not grab the next bit. And then you'll grab bits 34 to whatever 34 minus 17 is. Is that clear? Okay. So I keep putting more notes into that lab 2 HTML document. So I've just been adding to that each lecture. So I'll update that again right after this class, so it's available to everyone. And then if any other questions come up, just let me know. And I'll see most of you in 90 minutes.
If I can make one comment, if you use the nonlinear row on your single node test bench, you should see a frequency shift. You can test that totally on one node before you generate some giant drum.